Chapter 4 Pulse Modulation. To convert a signal from continuous time to discrete time, the value of the signal is measured at certain intervals in time. Each measurement is referred to as a sample. Analog to digital conversion by reading the value at discrete points, a process of taking samples of information signal at a rate of Nyquist sampling frequency. The original information signal can be reconstructed at the receiver with minimal distortion if the sampling rate in the pulse modulation system equal to or greater than twice the maximum information signal frequency. Fs is greater or equal to 2 FM max. These are the graph that amplitude over frequency for low-pass signal and band-pass signal. Undersampling rate below the Nyquist frequency. Undersampling leads to aliasing and the original signal cannot be properly reconstructed. Oversampling rate beyond twice the highest frequency component of interest in the signal and is usually desired. Aliasing effect. Undersampling sampling rate is too low to capture high-frequency variation. If the required condition of the sampling theorem that Fs greater than equals to FMMAX is not met, then errors will occur in the reconstruction. When such errors arise due to undersampling aliasing, natural sampling tops of the sample pulses retain the natural shape during the sample interval. Amplitude of frequency components produced from narrow, flat top sampling common used in PCM systems. Sample and hold circuit. The input voltage is sampled with a narrow pulse and then held relatively until the next sample is taken. Advantages: introduces less aperture distortion and can operate with this lower ADC. Analog pulse modulation, pulse amplitude modulation, PAM, pulse density modulation, PDM, pulse width duration, PWM, pulse position modulation, PPM. Pulse amplitude modulation, PAM. A PAM signal is generated by using a pulse train, called the sampling signal, or clock signal, to operate an electronic switch or chopper. A sample and hold circuit is used in conjunction with a chopper to hold the amplitude of each pulse at a constant level during the sampling time. Pulse duration, tau, supposed to be very small compared to the period, ts, between two samples. Lets max frequency of the signal, w, if on/off time of the pulse is same. Frequency of the PAM pulse is transmission BW of PAM signal. Bandwidth required for transmitter of PAM signal will be equal, larger to maximum frequency. Advantages and disadvantages. PAM advantage, allows multiplexing. Disadvantage, require a larger transmission bandwidth. Interference of noise is maximum needed for varies transmission power.
The slide discuss about pulse density modulation or pulse width duration. The width of pulses is varied in accordance to information signal. The amplitude and position is constant. The width of the transmitted pulse corresponds to the encoded data value. It immune to noise. The advantage of PDM is the noise performance better compared to PAM. The disadvantages are it require a larger power transmission compared to PPM and require very large bandwidth compared to PAM. This slide talk about pulse position modulation. The positions of the pulses are varied. The amplitude and width is constant. The higher the amplitude of the sample, the farther to the right the pulse is positioned within the prescribed time slot. The advantages of PPM are less noise interference, signal and noise separation is very easy, the transmission power for each pulse is same and the last one, less power compared to PAM and PDM. The disadvantage of PPM is it require very large bandwidth compared to PAM. This slide shows the modulating signal of PAM, PWM and PPM. This slide discuss about the advantages and drawbacks of pulse modulation. The advantages are noise immunity, relatively low-cost digital circuitry, able to be time division multiplexed with other pulse-modulated signal, storage of digital streams, and last one, error detection and correction. The drawbacks of pulse modulation are requires greater bandwidth to transmit and receive as compared to its analog counterpart. Special encoding and decoding methods must be used to increase transmission rates and more difficult to be recovered. And last one, requires precise synchronization of clocks between TX and RX. Pulse code modulation is a digital pulse modulation. Pulse code modulation is essentially analog to digital conversion. It represented by digital words in a serial bit stream. Sampling makes the signal discrete in time. The minimum sample frequency such that the signal can be reconstructed without distortion, fs bigger or equal to 2 fmax. Quantization makes the signal discrete in amplitude and round off to one of q discrete levels. Encoding maps the quantized values to digital words that are n bits long. Quantization is a process of converting an infinite number of possibilities to a finite number of conditions. Quantization is a process of assigning the analog signal samples to a predetermined discrete levels. Quantization is the process of rounding off a sample according to some rule. These figures show types of uniform quantization. Origin lies in the middle of a tread of the staircase-like graph in A, which is midtread, while for the midrise, the origin lies in the middle of a rising part of the staircase-like graph B. Most ADCs use uniform quantizers. The quantization levels of a uniform quantizer are equally spaced apart. Figures show that uniform quantizers are optimal when the input distribution is uniform. When all values within the dynamic range of quantizer are equally likely, the formula of dynamic range is dr equals to Vmax over Vmin, where Vmin equals to resolution. Dr is also equals to 2n-1. For answer in dB, you have to use 20 log dr. Now we proceed to the coding efficiency. The coding efficiency is the minimum number of bits divided by the actual number of PCM bits and then multiply by 100%. The process of quantization can be interpreted as an additive noise process, which is the quantization noise. The signal-to-quantization noise ration is given as average power of x divided by average power of nq. Now, this is the formula for the worst-case voltage SQR. SQR for a maximum input signal and the signal power to quantizing noise pow.R ratio. For the non-uniform quantization, it has unequally spaced level. The spacing can be chosen to optimize the SNR for a particular type of signal, as the graph shown. Non-uniform quantizers are difficult to make and expensive. First, pass the speech signal through a nonlinearity before quantizing with a uniform quantizer. The signal amplitude is then to be compressed. At the receiver, the signal is expanded by an inverse to the nonlinearity. This process is called companding. When the voice came into the compressor, the signal wave will be compressed to pass through the encoder. Then, the encoder transforms the wave into digital form in order for transmission. The wave is then go through the decoder to transform the wave back to its previous form. Lastly, the wave go through the expander to expand the wave back to its original form. Next, PCM encoding is the process of representing each quantized sample by in-bit code word where the mapping is 1-to-1 so there is no distortion introduced by encoding. Nonlinear encoding is the same concept as non-uniform quantization. It reduces overall signal distortion. This is also can be done by companding. The formula of PCM line speed is equals to the sample rate multiplied by the no of bits in the compressed PCM code. As we proceed, the channel bandwidth required to transmit a pulse is given by B equals to K in W. The channel bandwidth is also equals to transmission bandwidth. The spectrum of PCM signal is not directly related to the spectrum of the input signal. The bit rate R is equals to N multiplied by sampling rate. For no aliasing case, the minimum bandwidth of PCM is equals to R divided by 2N multiplied by sampling rate then divided by 2. Next, for PCM waveform generated by rectangular pulse, the first no bandwidth is equals to R or N multiplied by sampling rate. This is the flow of PCM transmitter or receiver. If the input analog signal is band-limited and sampled fast enough so that the aliasing noise on the recovered signal is negligible, the ratio of the recovered analog peak signal power to the total average noise power is as shown below together with the formula of the ratio of the average signal power to the average noise power. This is the effects of quantizing noise. If the PE is negligible, there are no bit errors resulting from channel noise and no ISI. The peak SNR resulting from only quantizing error is equals 3m square. The average SNR due to quantizing error is equals to m square. The above equations can be expressed as in decibels as 6.02 n plus alpha. Most important advantages of PCM are robustness to channel noise and interference, efficient regeneration, efficient exchange between BT and SNR, and lastly flexible TDM. This is the application of PCM in wired telephone. The voice circuit bandwidth is 3400 Hz. The sampling rate is 8 kHz. Each sample is quantized to 1 of 256. The 8-bit words are transmitted serially over a digital transmission channel where the bit rate is equals to 64 kilobytes per second. The bits are regenerated at digital repeater. The received words are decoded back to quantized samples and filtered to reconstruct the analog signal. Lastly, the PCM in compact disc. High-definition audio signal bandwidth is limited to 15 kHz. Nyquist rate is only 30 kHz. The actual sampling of 44.1 kHz is used to avoid unrealizable filters required for signal construction. The signal is quantized into a rather large number of levels, L equals 65536 to reduce quantization noise.